Welcome back. Today's topic is about solving Einstein's equation. This is rather a misleading title because there is no formal way to solve Einstein's equation. The title should be more like a exact solution to the Einstein's equation. This is a part of a course PH4205 at IISER Calcutta. In the last video, we have seen the Einstein's field equations. The Einstein field equations can be written as GAB, which we call as Einstein tensor, which is defined as the RAB minus half R into GAB is equal to minus kappa into TAB. Please note that there is a minus sign missing in the last lecture, so there should have been minus kappa TAB. However, it should not matter. We have not used it in any sense, but there should be a minus sign. This equation can also be written in a slightly different form, which is extremely useful. It is in terms of RAB. We can, same thing we can do on the other side and write it as a RAB as a minus kappa into TAB minus half T GAB, where TAB is a trace of energy momentum tensor, which is given as a T is equal to TA. That is a contraction of TAB with the GAB. So it's a straightforward to derive the equation from this to this. So it is extremely useful, especially when we solve the vacuum field equation or source-free solution, where this term becomes 0 and you have simply RAB is equal to 0, which is far more convenient than calculating one more step ahead and computing the Einstein tensor. Now, if we look at that, this side is a source which is written in terms of the energy momentum tensor, that is a density and pressure for the perfect fluid or whatever the field which you are putting. On the other side, we have a geometry which is given Ricci tensor, which can be written in terms of the metric tensor. So this is a second order nonlinear partial differential equation in terms of metric component GAB. There is no formal method to solve a nonlinear differential equation. This is also the partial differential equation. There is a separability issue also. Unlike the Poisson equation, which is linear, which we know how to solve given the boundary condition, there are methods which are mainly include separating the variable and reduce it to ordinary differential equation and then solve them. All the linear differential equation can be solved using the method with suitable boundary value problems. However, when you have a nonlinear differential equation, you do not have such a method. One of the main difficulty there is a linear superposition is no longer valid. That means in the linear case, when you have a linear superposition of two solutions, that is also a solution to the differential equation. However, that rule does not hold for the nonlinear differential equation. Sum of two solution or the linear superposition of two solution need not correspond to a solution of nonlinear differential equation. All in short, there is no formal method to solve partial nonlinear differential equation. Now, Einstein himself realized and thought that it is not possible to solve his own equation, and he basically stuck to what is called the linearized equation. Some portion of it we have done. We will have a look at the more of it later, but all of his calculations involve the linearized theory to predict the outcome of general theory of relativity. Now, few words about the sources. We can have various type of sources. One of the most interesting ones or simplest ones are the what we call is a vacuum solution or the source-free solution, where TAB is 0, where the geometry changes because of there might be some source outside your region of interest, and that produces the space-time curvature. It is similar to solving the Poisson equation or a Laplace equation to get the electric potential due to the point object. A similar thing can be done in the general theory of relativity too. In this case, Einstein's equation simply reduces to RAB is equal to 0, and then you can solve. You can use a fluid as one of the source. This is where the relativistic stars and all can be constructed. Stars are assumed to be fluid, which is balanced by the pressure due to the various nuclear fusion or the degeneracy pressure, where the gravity acting inwards. For the perfect fluid, we have seen that the energy momentum tensor is given as a TAB is equal to rho plus 3p UAUB minus GAB into P. So we have also seen that the divergence of this vanishes leads to Euler equation, which we call a fluid equation. So that's need to be satisfied for all the fluid which you are assuming. Now, fluids can be of two types. You can have a time-like fluid, that is a normal Newtonian fluid, which we call where the 4 velocity UA is a time-like. This describes how the fluid element flows, and what you have is a material flowing along a time-like curve, and then that describes the fluid which is time-like. You can also have a relativistic fluid which follows what we call is the equation of state, rho is equal to 3p. This you might have come across in your statistical mechanics, how to construct the equation of state for the relativistic fluid and how to compute the pressure given in terms of density. Now we can also have a perfect fluid dust where we have P is equal to 0. That is, we also know that it glows along the geodesic, and that is another kind of an interesting fluid. Now we see that in addition to relativistic star, we also have a universe filled with the perfect fluid. It can have a radiation, or it can have a time-like fluid, or it can have a dust solute. There are various cosmological models with all these as a perfect fluid that we come back when we handle the cosmology part of course. We can have a electromagnetic field as a source term. We know that any energy and momentum would give rise to the curvature of space-time through the energy momentum tensor. If you have a electromagnetic field, then that would also give rise to curvature of space-time. Now, so produce the solution to the Einstein's equation would also affect the particle without charge. When you have a charge, you essentially have a Lorentz force equation satisfies in the curved space-time. But the neutral particle would be moving along the geodesic produced by the curvature produced this energy momentum tensor, which can be written in following manner, which we have seen in the previous video. In this case, the equation, the field equation is called the Einstein-Maxwell's equation, and we have a solution coming from the electromagnetic field, and the space-time geometry is changed because of presence of energy in the electromagnetic field. Now let's quickly look at how we can get some exact solution. Basic idea here is a reverse engineering. In absence of a formal method or algorithm to solve the nonlinear partial differential equation, one can construct the solution based on the physical intuition, or what we call is a reverse engineering. First, we assume the form of metric with the suitable symmetries so that the solution physically makes sense. Once we construct the metric tensor or the form of metric tensor, we can substitute that and calculate the Einstein's equation, or rather we start with the metric tensor, then we compute the Christoffel symbol, then we construct a Riemann tensor. We can cut short and directly go to the Ricci tensor. We can compute the Einstein tensor, or we can simply use the other form of the Einstein's equation using the Ricci tensor itself, and then we construct the energy momentum tensor. Now we look at that energy momentum tensor and see whether physically that does make sense or not. We see whether it is a perfect fluid, whether it is a electromagnetic field, or something physically which we understand. Then we have an exact solution to the Einstein's equation. There are various physical symmetries which allows us to construct the form of the metric tensor. Some of the popular symmetries are spherically symmetric, which is field outside the spherical star or the spherically symmetric gravitating object. We could have actually symmetric or azimuthally symmetric. These are the stars which could be rotating, or you might have some rotating frame, and a similar gravitational field would give rise to the azimuthally symmetric solution. We can have a constant curvature. We have, that is one of the cases where everything gets simplified. We can simply write down the Riemann curvature in terms of the metric tensor itself, and that would also give rise to interesting solution, and one can construct a solution. The other thing is what we call is asymptotically flat. When distance is very large, r tends to infinity. In the case of spherically symmetric case, what happens to metric? Whether metric goes back to Minkowski metric or whether it takes some other form. So that would say that asymptotic form of the metric, that also can be imposed on the metric, and then we can solve. Let's quickly look at how do we solve for the spherically symmetric solution. We have a first solution to Einstein's equation was formally given by the Karl Schwarzschild. It was thought that relativity is extremely complicated subject and not many would understand. That is the kind of idea we have had. The Eddington, one of the British astrophysicists who were constantly in contact with Einstein throughout the development of relativity, once said that when some press person asked him, apparently it said that 3 people understand the general theory of relativity. Is it true? Then the Eddington, in his old British arrogant way, said that who is the third one? So is to say that we have a German astrophysicist, Karl Schwarzschild, actually gave the first exact solution to the Einstein's equation within few months of the Einstein publishing his work on general theory of relativity. He solved the what is now called the Schwarzschild solution is a spherically symmetric space-time. There is a sad story about the Karl Schwarzschild who had to go to war immediately after he solved this equation, and in the war he died because of some infection. So he never came back to the real world. His story is ended in the war. However, this solution is one of the most famous solution to the Einstein's equation, because most of the stars systems are considered to be spherically symmetric, and that is one of the most important solution to the Einstein's equation. So mathematician, in fact, who understood the Riemann geometry could solve the Einstein's equation. And the geometry in this case is a spherically symmetric. That is, you have a 4-dimensional space-time which is represented as a r cross s2. That is, you have a time which go along a real line, and then you have a radial coordinate which is again a real line. Then you have a 2 spheres. That is what the spherically symmetric geometry represent. In this case, we have t is equal to r is equal to constant represent the spheres. So that is what we have is a geometry, and we can assume the time independent solutions. Take the static solution, what we call is a metric is independent of time, and then see what kind of a solution we get. Only 2 components of metric which are non-trivial, that is G00 and G11. Both are assumed to be the function of R only. So the general metric for this spherically symmetric space-time can be written as a ds square as a e to the power nu of r dt square minus e to the power minus lambda r dr square, and then you have a length element on the sphere which is r square d theta square into sine square theta d phi square. Please note that this is the style in which relativists write. They simply don't write f of r and g of r to solve this metric component. They write as a e to the power nu lambda. Sometimes this simplifies the calculation, sometimes it doesn't. It is a useful notation when you are doing the calculation with your hands. However, these days people use algebraic softwares, and then that doesn't really matter whether you write it in this form or any other form. There is a one advantage writing in this form. When nu is equal to 0 or lambda is equal to 0, 0, then the metric represents the flat metric. So that is one of the advantages. And then the sign simply does not change of this. So the metric signature is maintained. So whatever you do, this function remains positive, so that one does not have any confusion regarding what we are looking at. Now we first solve for the vacuum solution, and then we look for spherically symmetric stars. But let's start with the vacuum solution. That is what is called the exterior Schwarzschild solution. And let's go step by step. The first we have to compute the connection. So we have a metric tensor which is given by the matrix as here GAB as all the diagonal forms, and then two non-trivial functions, and the rest are all metric on the sphere. So we need to evaluate these two such that it satisfies the Einstein equation in the vacuum, or simply RAB is equal to 0. So we can get the upper indices by simply taking the inverse. So inverse is e to the power minus nu. So that is another advantage of this notation. Inverse is simply e to the power minus nu. Inverse of the metric is obtained. Then we can compute the gammas. You have already done this with slightly different notation. Since you are already expert on this, I am not going into detail. So we have easily compute the non-vanishing Christoffel symbol, which are given by gamma 0, 1 is given by 1/2 nu prime. Prime is a derivative with respect to r. That is the only variable which is present. The other one is gamma 1, 0, 0, which is a bit of a cumbersome. Otherwise, rest of the Christoffel symbols are given by gamma 1, 1, gamma 1, 2, and gamma 1, 3 it should have been. So there is a typo here, 1, 3. And then we have 2, gamma 2, 1, 2, and 2 ones are non-zero. Same way gamma 2, 3, 3, and then we have gamma 3, 1, 3, and then gamma 3, 2, 3, and gamma 3. So these are non-vanishing connection coefficient. Let's compute the Ricci tensor. There are many ways. You can first compute the Riemann tensor, or you can directly compute the Ricci tensor. Here is the expression for the Ricci tensor with the suitable expression to simplify everything. The first one remains almost same. The second one is because of the contraction between the gamma, which can be written as a derivatives of a determinant of metric, where the G is a determinant of metric. Minus sign comes because of pseudo-Newmanian nature. Third term remains same, and fourth one again get replaced by a derivative with respect to determinant of metric. So this is the expression for the Ricci tensor. One need to calculate this step by step. One of the difficulties here coming, these are straightforward. This is also straightforward. There is a one summation over here, other summation over here. That's the most cumbersome. Then you have a one summation over here. So these have to be done. These are fairly straight. Let's compute the square root of G. In this case, it is a product of diagonal element. This can be simply written as e to the power half nu plus lambda r square sine square theta. Now let's compute the R0, 0 component. I am doing only one, leave the rest as an exercise because that's going to take a long time. In individual terms have to be calculated. Here simply put explicitly 0, 0 for AB, that is R0, 0 is a derivative of gamma C0, 0 with respect to xc, and the derivative of square root of G with respect to x0 second order. So this term is going to be 0 because metric is not dependent on time. There is no need. So that term is 0. The next term have to be summed up over LRT. These two also have to be summed up. So that is one term goes away in this simplification happens. And then when we look at that, only term of type gamma A0 is gamma 1, 0, 0. So that is the only non-vanishing term. But that for computing this, we simply get derivative of gamma 1, 0, 0 with respect to x1. Then we have the term which is a 2 summation over the indices C and D, but some simplification do happens. And then this because of gamma only 1 here, so x1 is given by this. We can expand the indices. Then you see that there is a whole lot of list, but again we eliminate 0 component and keep only non-zero component. the last one you have written. So this is a summation which need to be done. So again, we see that the sum of the terms goes 0 because there is no gamma. They are all 0 with that form, and then we left with only 2 which are same. That is what we have. Then the last term which we need to handle, so that is take the differentiation of this term, and we now explicitly substitute the form of metric and compute the values, and then see what do we get. So first one is a differentiation of gamma 1 0 0 with respect to r, and that is what we have, and that can be further expanded and written in terms of first and second derivatives of nu. And then the second term requires the computation of this derivative, that also can be easily done. So what we have is another long term which is a derivative of square root of g, because it has dependent on the r, so that need to be differentiated. When we computed gamma in our one of the tutorial, we have assumed G00 and G11 is a inverse of each other. Here we are not assuming that, we are actually showing that that condition is valid for the vacuum solution, and that is we will see. We have computed all the Ricci tensor, at least I have computed one, and you can do it rest of the thing, that is I am giving it as a homework. It's a similar but a long calculation. One obtain R00, R11 again in terms of the first and second derivatives of gamma, and there is also a first derivative in lambda, and then you have a R22 which is again comes as a first derivative in lambda and nu, and then R33 which is again has this similar term. These two equations are similar to each other, R00 and R11, R22 and R33 are similar to each other. If we want to solve the source-free equation, we set all of them to 0 and then try to see what kind of differential equation we get for nu and lambda. Now let's look at these two. They are essentially same, and then you get a simple differential equation, r into lambda prime minus r into nu prime plus 2 into e power lambda minus 2 is equal to 0. So that is the equation we get, and then R22 equation is a second order differential equation in nu and the first order in lambda. And similarly, R00 also gives the very similar term, but except minor changes here. So second order differential equation in nu and the first order differential equation in lambda. Let's call them equation 1, 2 and 3. The fourth equation is same as 3. Comparing these two equations, it is straightforward to see that when you sum up equation 1 and 2, you will be left with the simple equation that the nu prime plus lambda prime is equal to 0, or in other words, nu prime is equal to minus lambda prime. So this is exactly what it says, is that the G00 and G11 are an inverse function of each other because they are exponential function. Their value comes with the minus sign, and that is what we see. They are producing the inverse of each other. Now we can substitute this condition in equation 3 and try to simplify it further. Now we get a differential equation for nu or lambda. Both one can solve depending on the convenience and the form. Both are very similar. There is no big difference between them. One need to solve this differential equation. I believe you guys are expert in solving the first order differential equation. The first order differential equation can be always be solved in some way or other way. If not anything else, integrating factor should solve them out. But in this case, solution turned out to be rather simple. E to the power nu is equal to 1 minus a by r, where a is a constant. That constant need to be determined based on the boundary condition, and the boundary condition which we have is two things. One is r going to infinity, the g nu nu should become the flat, or it should become a Minkowskian metric. That means that condition is automatically satisfied. In addition to that, we also have G00 can be written as a 1 plus 2 phi. That is a Newtonian approximation. When R is very, very large, G00 can be written as a 1 plus 2 phi, where phi is a Newtonian potential, which we understand is as a Gm by R. That is a potential due to a point mass at R is equal to 0. And when we compare with that, we get A is equal to 2m. Of course, we have assumed G and C is equal to 1. If you do full calculation, then you would have that as a Gm by C square. M is missing there, M need to be there. So that is what the solution we have. We have G00 is equal to E nu, that is a 1 minus 2m by R, and G11 is equal to e power minus nu, that is 1 minus 2m by R to the power minus 1. This is what we call is a spherically symmetric vacuum solution, or popularly known as a Schwarzschild solution. Length element for a Schwarzschild solution can be written as a 1 minus 2m by r dt square minus 1 by 1 minus 2m by r dr square d theta square minus r square sine square theta d phi square. So this is a what you call is a Schwarzschild solution, which Schwarzschild produced within 3-4 months of Einstein publishing his work on general theory of relativity. So this is the first formally known non-trivial solution to the Einstein's equation, and that is of astrophysically importance, because most of the time in astrophysics we assume spherically symmetric, and that is why this plays a very fundamental role in understanding general theory of relativity from the astrophysical perspective and even from the theoretical point of view. We will study physics of this solution in coming lecture. However, we focus on solving couple of more type of Einstein's equation before really going into understanding how to do physics on a given space-time, which is a solution to the Einstein's equation. So this solution is known as a Schwarzschild solution. Now is a homework part. Deadline is on 27th March 2021 at 6 p.m. You should submit this on VLOG. So the form of the metric is given here, which is what we have used in calculating the Riemann tensor. So you will have to compute all the non-vanishing component of Ricci tensor RAB and solve the source-free Einstein's equation and obtain the metric. So this is going to be the exercise, basically working out through the solving the Schwarzschild solution. Some portion I have left, but it can be easily done with carefully going through the algebra. I'll stop here and continue with the spherically symmetric star with the perfect fluid as an energy momentum tensor in the next video.